2025 and this hasn't been done already? I mean, do we not know where the forests are?
A lot of the information that we want about the natural world has never been recorded like that on paper necessarily. You know, where all the different species of trees are, or where the habitats are, or where the boundaries between, you know, the rough grassland and wetland are. So we need to actually create that information for the first time.
Thing is, I can see the potential for this in terms of scientific interest, but I do wonder whether, let's say, we get to a point where you can understand what dolphins are saying, communicate with the higher animals on the planet. Does it change how we view ourselves and our place in the world?
I think it absolutely has that potential.
Welcome back to Google DeepMind, the podcast. I'm Professor Hannah Fry. Now, we focus a lot in this podcast on AI and its interactions with humans. But there is another story that's unfolding, one in which AI could help protect our planet. Think oceans and forests and deserts and fragile ecosystems, and the millions of animal species that are crawling, swimming, and flying across this earth. AI has the potential to tackle one of the biggest challenges of our time, the damage to nature and ecosystems. But with a problem that's this vast, where do you even begin? Well, Drew Purves, nature lead at Google DeepMind, is my guide through the rich terrain of AI for nature. He has got 2 decades of experience in ecological research and has been at Google DeepMind for almost 10 years now. Drew, thank you so much for joining me.
Oh, thanks. It's great to be here.
I think most people probably agree by now that the environment is an important aspect of our future, something that deserves preserving and looking after. What's holding us back in this area? What's making it a difficult problem?
The short answer to that often is lack of information. So you're right, you know, there's this groundswell now of agreement about the importance of biodiversity, ecosystems and nature. And then we have signs of action in different sectors, in the private sector, in the government sector. You know, if you look at some of the numbers, for example, I mean, there are 189 countries around the world that have signed up to the 30 by 30 plan, which is to protect 30% of ecosystems on land and in the oceans by the year 2030. So there's so much to feel good about. But often when it comes down to actually taking action on the ground to either protect or restore biodiversity and ecosystems, there's just a lack of basic information.
So what are the big questions that AI could help answer in this space then?
I mean, there are a number of them, obviously. But for example, if you're thinking about a protection scenario, protecting biodiversity, you need to know where the biodiversity is. It might be focal species, or it might be biodiversity hotspots, and so on. It might be particular endemic species. If it's a restoration scenario, you want to find particular places around the world that are have the highest potential for ecological restoration. But for example, you might need to know which species of trees to plant or which species of animals to reintroduce. So down at this local level, it's because biodiversity is so place specific, you need that locally relevant information for, you know, communities or whatever local action is happening to guide the action down there, and often it's just missing.
Is that the big goal then of Google DeepMind using AI in nature to really fill in the information gaps in the same way that we have done for the human world?
Well, here at Google DeepMind, we're growing a portfolio of work around AI for nature. And there are at least 3 key categories of AI for nature to explore. So the first of those is AI for data, and that can mean bringing in data from the field, from things like cameras, microphones, and so on, or identifying and bringing in data from the literature, because there's a huge amount of data there. The second category, though, is taking all of that data and combining it with lots of other sources of data, like satellite data and so on, to create that derived information that decision makers need to protect or enhance nature. And then the third category, which is easy to miss, is that all the information in the world is fine, but human beings can get overwhelmed by that amount of data. So then there's this key role for active deployment of AI to help decision making, to help people make sense of all that data.
And that's, I guess, in part because, you know, this is sort of quite a new area, right? I mean, this hasn't been around for as long as some of the other applications of AI. It's not as obvious of how to sort of solve biodiversity as it might be to solve, you know, disease, for instance.
I think that's true. It does feel like a growth area in AI. It's kind of interesting, actually, that ecology obviously has a long history, but interestingly, mathematical ecology and statistical ecology and even machine learning ecology has a long history too. Fisher, for instance, the famous Fisherian statistics, a lot of that was developed in an ecological context. I think that's because ecology is inherently quite challenging. Like there's no obvious way to sort of record and frame ecology. You've got a vast variety of species. You've got processes operating at different scales. The temporal signals are always really noisy. And so it's interesting. It's always been a little bit of a sort of challenging domain that has led to innovation in statistics and machine learning. And so we very much expect that in the work we're doing now, trying to apply this deep learning, for instance, the recent AI revolution to ecology, that also will be a way to innovate.
Okay, well, let's dig into some of this stuff then. So in particular, in that middle layer, right, of like taking in data and sort of deriving something from it. Because, I mean, a lot of this involves mapping, right? Like a sort of that fundamental stage. Tell us a little bit about mapping the biosphere.
So many of the decisions in environment and ecology come down to place. And that's because in ecology and biodiversity, each place is so different species, different habitats, and often different issues that you need to deal with, you know, whether it's agriculture or wildfires, etc. So all of that missing information I mentioned before, most of the time it's missing geo information. And so very simply, you can think of that as like maps, you're right. And so we need to map habitats. That's kind of the substrate over which ecology plays, because substrate is largely defined by plants. So habitats and plants are closely related. So, you know, whether that's forests, grasslands, etc. But of course, then we want to map all the species. Ideally, that's a very challenging problem just because there are millions of them and a lot of them are very small and can't be seen and so on. Of course, there's maps for now, but also we might want to understand historical change. Those baselines of change are very important. And of course, being able to project maps into the future, which is a whole different challenge. All roads lead to maps in ecology.
Okay, that's interesting. I'm sort of surprised that this doesn't exist already, though. I mean, can you not just get this from Google Earth?
It's a really interesting question because we've got so used to it. Of course, it's been amazing, the geographic information we have through things like Google Earth and Google Maps. You know, real human achievement to bring all that together and make it available. But it's very human-centric so far, that data. So, of course, we've got roads and you've got every shopping centre, you know, every post office, everything like that. But actually, it's much less developed in terms of mapping the natural world. So it's
focused more on people than the environment.
Yeah, that's right. A lot of the information that we want about the natural world has never been recorded like that on paper necessarily, you know, where all the different species of trees are, or where the habitats are, or where the boundaries between, you know, the rough grassland and wetland are. So we need to actually create that information for the first time.
It sort of seems a bit bonkers to me that we're in, 2025, and this hasn't been done already. I mean, there are sort of attempts at this that exist. I mean, Landsat was developed in the 1970s, right? Of like taking satellite images and categorizing different regions. I think there was some stuff before that for military purposes using satellite images. But is this just at a different scale to those things?
It amazes me too. One thing that amazes me is that the satellites even exist. I mean, that's incredible, right? It just blows my mind that actually for many decades, you know, we've basically had these like floating high-res digital cameras looking down at the Earth for decades. That's absolutely incredible. It's also incredible the amount of geographic information we actually do have. There are amazing data sets or amazing maps of all kinds of things that are relevant to the environment. And yet at the same time, sometimes you come in with the most basic questions like, where are the forests?
Do we not know where the forests are?
That's right. And honestly, it surprises me too. But we don't have gold standard accepted global maps for most of the habitats that we need to understand, including forests. So there is no absolutely universally accepted gold standard for forest, non-forest. Now, having said that, there are some pretty good ones nowadays appearing, but there's still room for improvement. On the other hand, what we're looking at is, even if you had that to guide decision-making, you often need to distinguish different kinds of forest. For example, the most basic split, natural forest from planted forest. And there definitely isn't a gold standard accepted map for that. And some of the work we're doing at the moment is trying to do our best to provide the best yet available map of that. We call it the Natural Forests of the World project.
Why are forest maps useful? What can you use them for?
Well, forests are incredibly important, harbouring biodiversity and carbon. And for that reason, there's a lot of government policy and a lot of international regulation around forests. And forests are a major focus of concern for conservation groups. And in all cases, they need the best maps so they can know where to protect if they're looking to protect forests, where to potentially restore forests, where to monitor for problems like forest diseases, and on and on.
Can I see it? Have you got it?
Yes, I have. So firstly, what we produced is a map for the whole globe at 10-meter resolution. So each 10-meter pixel is classified, and we give it a probability that it's natural forest.
I should probably do a little audio description for the people that are listening rather than watching. We have essentially in a browser what looks superficially like well, exactly like Google Earth, but overlaid on top are these teal-coloured pixels that align, but not exactly with what you can see to be trees from the satellite images.
That's right. So you can illustrate that, for instance, and this is why it's so important, but also difficult to tell the difference between natural forest and planted forest, because the natural forest will typically be much higher in biodiversity and often carbon if it's somewhat old growth. So this will be an area that you would tend to want to protect more. And then equally, if you detect forest loss, then the loss of natural forests will typically be much more concerning than, for instance, the loss of planted forests, many of which are planted in order to cut them down, like a timber, so they can actually be sustainable. But in this case, in the southeast US, for example, there are a lot of loblolly pine plantations, for example. So these are a type of planted forest which is planted to give timber very quickly after about 5 years.
Okay.
And so you can see there we've got a mix of areas that we classify as natural and areas that we classify as planted forests.
Yeah.
And if you zoom in and out, you know, most of the time, of course, there are inaccuracies, but we're over 90% accurate when we test it. So you can see here, as we fade up our predictions there, then if we look at those remaining parts and you go in, you'll find these neat rows, and that's telling us it's planted forest. So to be able to do this at scale, yeah.
So, okay, I noticed in this example that you have, it's sort of natural forest, not natural forest, but I also noticed that you've got a confidence threshold there.
Yes.
So are you sort of classifying this with a probability rather than just saying, yes, it's natural forest, not?
Yes, we are, and it's something we're quite passionate about, really, because there is a tendency, if you see a map that is classified like in a black and white like way, to believe that, you know, and even if it's relatively accurate most of the time, it's really important to be aware of the inaccuracies. And so that's why we much prefer to present things as this uncertainty map. Now, of course, one thing you'd often do is to think, okay, I'll choose some threshold then, which I will use for my purposes to distinguish forest and non-forest. But depending what you're after, you may choose different thresholds. So if you were really looking to make sure you're protecting all of the remaining natural forest in an area, you would set your confidence threshold. It's actually setting it low so that you pick all of that up. But of course, you'll also pick up a whole load of planted forest, but you sort of don't mind along the way. Whereas on the other hand, if you had very limited resources, let's say, and you wanted to verify that the loss of natural forest had occurred and you can only afford to visit certain places, you may put a very high threshold on it to make sure that you're really visiting the places where you're most confident about and so on. So we're sort of providing that to downstream users in this uncertainty form. We're open sourcing all the maps, we're open sourcing actually the data and also the new models we developed, open sourcing out to the community. And what it means for downstream users is that they can get to their own high quality remote sense maps with much less compute than before, lower data requirements, and all importantly, lower skills requirements as well. So if we do it right, something like that can really help to democratize remote sensing on the outside.
In terms of what's going on behind the scenes, I mean, you're using a vision transformer, right?
Yeah.
How does that work?
So overall we're doing is bringing in this massive satellite information. So these are enormous images for a start, the sheer number of pixels. And then for each pixel, it's not just RGB like it would be with an image, but it's often many different bands, infrared, etc., all these different bands. And those bands are going up through time. What? Then you've got multiple satellites. Each satellite is giving you records every few days. You have a lot of missing data from things like clouds. So you need to take this enormous amount of data and somehow crunch it all down to pull out the thing that you actually want to know, like, is it a forest? And the model in the middle that we're using is this vision transformer model.
Transformers are sort of, people usually associate them with large language models, right? Like, you know, paying attention to different bits of sentences is more important than others. How does it feed in when it comes to maps?
That's right. So transformers were mostly developed to work on language, and this idea of these attention heads and so on. They were then adapted into vision transformers to do similar things on images, attending to different parts of images. What we've done here is then expand that out to a special vision transformer that's set up to deal with the challenges of satellite data. So it's actually now a multimodal, temporal, spatial vision transformer. But it's still a form of vision transformer. It's a great story about how you can get this exchange of methods between different areas, from language modeling into vision, and in this case, into remote sensing and out there into environmental policy.
So it's paying, when it's working out whether it's forest or not forest, it's paying attention, as it were, to, sometimes the infrared data, sometimes the image, sometimes the sort of the topology of the area, that kind of thing.
That's right. The transformer architecture is an extremely expressive architecture that gives the model a huge amount of freedom to choose what it attends to and how it then combines that information downstream into its prediction. And that's particularly valuable in an area like remote sensing, where you've got such a wide variety of modalities coming in and the all the data sets are so huge. And so it's an area that really benefits from this kind of extra sort of expressivity and flexibility of the model.
But that expressivity in the end comes down to forest, not forest.
That's what's funny, right?
Yeah.
All of that gets crunched down into just that, in this case, that single map.
Well, okay, I'm just picking up on something that you said in your answer there, because you were talking about how you have these satellite images over time. So then, rather than just mapping where the forests are or aren't, does that mean that you can look at how the forests are changing?
Yeah, that's a very important point. Yeah, indeed. So the interesting thing with remote sensing and satellite data is because the satellites have been up for years, if you can do this mapping, you say you take 1 year's worth of satellite data, say for this year, and we can see where the forests are this year, we can automatically redo that from the past to estimate the picture of change. And this is really important. There's a project called Global Forest Watch, which Google has supported before, that does this. And so you can, each year, the latest map comes out and you can look at the changes in forest cover through time. More recently, we've created this stack of maps that we call deforestation drivers. And what this is actually looking at is it's taking each unit of forest loss and categorizing the cause of that loss in terms of logging, agricultural expansion, and so on and so on. But we've applied that for the last 20 years. So we have 20 years of not just deforestation, but 20 years of the causes of deforestation. So in collaboration with our colleagues at the World Resources Institute at WRI, we've worked up this global map of the causes of deforestation for each year from the year 2000 to today.
And what do you find when you do that?
It's really interesting to look at these patterns.
Go on, show me. I know you've got it. Cool. I know you've got it. I want to see it.
So the first thing you can see when you look across the world is that there's forest loss everywhere.
Yeah, quite a lot in Northern Europe.
Yes, for example. So it's so easy to think that all of these problems are just occurring in the tropics or in the global south. Right, exactly. And the second thing, though, is the causes of the loss does change between different regions. So if you have a look at, zoom in on Brazil here in South America, you can see, you can go right in.
But
and see
lots of permanent agriculture.
That's right. Yeah. So this sort of darker yellow colour, and you'll find, when you fade in and out, you'll often find that this is associated with clearings and so on. So you can see how that's working.
You can literally see how it picks out the edges of fields effectively.
That's right.
Yeah.
Because all that fine-grained data is actually in the satellite signals, right? But there have been previous maps, but this one is 10 times finer resolution. And that's what really enables you to pull out these local patterns. And that's where a lot of the decision-making happens, is at local scales. And so understanding things at local scale is really important.
Putting all of this together, if you're sort of, long into the future, right, is there like a real-time aspect to this? Could you prevent illegal logging from happening before it did?
It's a really good question, because the work that we've been talking about up to now tends to be taking satellite data from an extended period to estimate how things were either right now or looking into the past.
Retrospectively. Right.
Whereas this idea of rapid real-time alerts and then also longer-term future forecasting is some of the real growth areas for us. There are already actually existing organizations that are using satellites to try to pick up deforestation alerts live. So that actually exists. One of the challenges, though, is that in order to pick up most of the real deforestation, they've had to use a methodology that picks up a lot of false positives at the same time.
I see.
So it's actually really challenging. So there's so-called deforestation alerts. It's an incredible achievement, but at the same time, it feels like that could be improved. So obviously, if we could get it down to the point where the alerts were much more accurate, then it would be much more easy for people to act on them.
I guess this goes beyond just satellite data then. I mean, you have to start working in other types of data, wouldn't you?
Yes, I think so. I mean, the interesting thing is that you can produce a model of change and you can train that on past data, and you can do that very scientifically, and you do all of your held out data and your validation and all that clever machine learning stuff. The problem is, on the other hand, that the whole thing around climate change and environmental change, the future is different to the past. So how can we be confident that we can reapply that model into the future?
Like, this isn't like, predicting the weather a week in advance. It's the whole underlying model is different.
That's right. And when you look at, say this process of deforestation that we've been talking about, I mean, that is a human-driven process. And humans can change behavior very, very quickly in responses to things like changes in the market. Perhaps the price of soybeans goes up, and then that encourages more rapid deforestation. On the other hand, government regulation and policies, or local regulation and policies, and so on. So the traditional machine learning approaches are going to really struggle to deal with that, because they can only deal with numbers and they can only deal with the past. And I think that's one of the reasons why we're really excited about hybridizing, in a sense, the best of the scientific tradition of simulation modeling with the machine learning, data-driven approach to forecasting with actually things like the large language models like Gemini, which potentially could pick up on, changes in government policy, news, media, perhaps integrate together things like agricultural prices and so on to help us at least to slightly adjust and identify some of the sort of uncertainty scenarios around those future predictions.
If that's vegetation, though, if that's like trees and hedgerows and shrubs, what about, we also care quite a lot about the creatures that are living inside them. How do you bring that in?
So habitats is one thing, but then most species are not visible from space and they don't form a habitat in that sense. Instead, it's all the insects, the fungi, the birds, etc. And so much of our concern around biodiversity and so much of the action around conservation is actually around those species. And so you looked surprised earlier when you said there isn't an agreed map of forests, and that's true. But that's also true for most of the species in the world. Now, again, it's really important to realize everything we're doing in ecology and biodiversity builds on this huge foundation of organizations and hard work from the past. So there's an amazing organization called the IUCN that does provide maps for 140,000 species worldwide. So it's amazing. On the other hand, those maps are very coarse. They're driven by expert opinion. Those experts, they really know what they're talking about, but necessarily they're quite coarse maps. So 50 kilometre or so cells, and they're only refreshed about every 10 years.
Oh, wow.
But there's an obvious potential role there for producing, in theory, much better maps using the latest in AI and remote sensing and etc. So we're sort of exploring that as well.
Okay, but then how do you do it though? Because you haven't got the equivalent of satellites, in space photographing insects.
That's right. You could view it as a sort of prediction problem. What you're saying is the signals I do have, like the satellite signals and other input data, can help me produce a sort of probabilistic estimate of how likely something would be there. And there's probably always quite a large residual uncertainty on that. So how do you go about doing that? Interestingly, at the absolutely coarsest level, it's kind of the same old, in a sense, machine learning approach. In other words, you take your training data and you take your input data like the satellites and you bring in a special model and you fit the model and you get the output and you evaluate it. This is the classic stuff. But in this case, it's really challenging because the data we're bringing in mostly is citizen science data. So this is people out in the field noticing a bird.
Something,
That's right. There's an incredible platform called iNaturalist. It's on your phone now. And if you see something, you can take a snapshot of it and then you can upload that to iNaturalist. And iNaturalist actually have their own machine learning models, so they can classify that image to species, which is fantastic. And this is now the main source of these on-the-ground observations of species globally is coming from this amazing phone app called iNaturalist. So that's fantastic, but actually that data is still very biased and patchy.
Why?
So, for example, people typically are close to their home when they take a picture. So where people go, when they go, they'll typically go on a nice day, and also what they choose to look at and take pictures of. So what you'll find is you'll get lots of pictures of brightly coloured birds close to cities on sunny days.
Right, I see.
And what you don't get is many pictures of, small brown mushrooms in remote places when it's raining. And although I'm joking about that, there's actually a much more serious element to this too, which is when you look globally at the distribution of citizen science data, there are major areas of the world with very little, sub-Saharan Africa, for example, because actually iNaturalist depends on having a certain amount of leisure time really to do these sorts of activities.
Yeah, and also, speed of internet connection and quality of your smartphone camera.
That's right. And this is a real irony then for two reasons in a way. One is from the fundamental ecology. If you weren't careful, if you were naive about it, you would conclude that all species like to live near to middle-class neighbourhoods on the edge of cities, right? Because that's where most of the data is. And then globally, there's a real irony there, which is we're lacking data in many of the places that have the most biodiversity, in many of the places where the current threats to biodiversity are the greatest, and where people's livelihoods depend most on biodiversity, which is just kind of awful, right? And so the magic, in a sense, that we're looking for from deep learning in this space is to see if we can somehow generalize from this very patchy bias data that we do have to ecologically plausible distributions for all of the species worldwide. And that's a big challenge. And at the moment, I think you would say the jury's out as to whether it's possible. But we are seeing some evidence of that.
But does the things that you've learned and that you now sort of know, in inverted commas, about the vegetation then feed into where you expect the species to be? Does one sort of help the other?
Firstly, that's a really good point that, we know enough about ecology to know that actually things like climate and elevation and habitat are very strong predictors of species. So you're absolutely right. We've already talked about the fact that we can classify habitats from space down to a fine grain. So that itself we would expect to be highly predictive of which species are there. So then bringing in all this observation data, then we can look at the overlap between these in the areas where we do have data and hopefully pick up a general enough understanding to then be able to reapply that globally. Because there is another challenge here, which is you have these long tail distributions in ecology all over the place. You have a few common species and then lots of very rare ones. So we need to do the same thing across the taxonomic sort of tree of life, that can we learn the key relationships for the more common species that are data rich, enabling us to make the best predictions we can for species that are actually fairly poor, data poor. So if we can learn about, so for example, if we bring in species trait data, we might find out that in this part of the tree of life, let's say, it's the larger bodied species that tend to live in the colder environments. And we might be able to discover laws like that in places where we do have lots of data, like Europe and the US, in a way one day where we can apply that with a certain level of confidence in areas where we have much less data, like the global south. Not that we'd ever have a blind guess, but what it would really do is lower the data requirements in those areas. Once we've learned some of the more general rules, it would mean that actually a relatively small amount of observational data may be enough to sort of anchor the distribution of that species. It's such an exciting space.
I do wonder about other types of data here. I mean, you're talking about data about the landscape, about elevation, about the vegetation. But are there other elements of data, like photographs, for instance, that you can also bring in here?
Yes, there are. And that, in general, you could think of that as this trend towards multimodal models and multimodal AI. And that particularly lights up, I think, in the world of ecology and biodiversity science. So because you've got such a wide variety of organisms at different scales, and so different modalities suit monitoring different kinds of species. So they're talking there, you've got images that, let's say, humans take deliberately with a camera, like they're the ones that say iNaturalist specializes in. Often, though, say in the Serengeti projects and others, we're talking about so-called camera traps. These are cameras that are motion-activated cameras. And a lot of the time, they've got infrared lights on them. So they're actually taking infrared images at night. So even images are, there are different kinds of images you can take. You've then got aerial imagery, let's say from drones or from planes. You've got the remote sensing satellite imagery we're talking about. And then also you've got bioacoustics, so-called bioacoustics is where you're deploying microphones in the field. That might be familiar to a lot of people watching this, for example, around the apps that identify birdsong. Merlin and eBird and similar.
Because those already exist. I mean, I've played with them a little bit, right? Like you're outside, you turn it on, it tells you what birds you're listening to.
That's right.
But that's supervised learning, is it, that manages to do that?
Yeah, that's right. So you need, in all of these areas, you need a sort of what we call a corpus of labeled data to start with. So you need a picture with a label along with it. This is a monarch butterfly, or this is a
crow squawking.
Yeah, exactly. All of this sort of stuff. And with enough of that, you can then train a model that generalizes. So that's what's called supervised learning. That's right. And that's powered most of these developments in each of the individual modalities. Whether that's images, remote sensing, etc. Yeah.
You've got a project though called Perch, right? Tell me about Perch.
So Perch is in this space of bioacoustics, and the idea of deploying microphones in the field is really attractive because there's almost always something making a sound.
Yeah.
And it's incredibly rich, the information we can extract from sound, actually. And you can leave the microphones out for days on end to record all that data. And of course, sound is not necessarily just species, but it can be behavior. We might be able to distinguish juveniles from adults. You might be able to pick up warning signals. So insects make sounds, reptiles make sounds, birds make sounds, mammals make sounds, and you pick all of that up. So you don't have to have line of sight to the organism either. It can work at night. So it's an incredibly promising technology for pulling out data from the field.
But if it's already been done, I mean, if you do already have these apps that can tell you if you're listening to a crow, then what else is there to do?
Perch is taking a slightly different approach. It's a foundational model for natural sound. And what that does is, like other foundational models, it's not out of the box. It's not just providing you with the ability to identify lots of different birds, for example. I mean, it does do that. But what it's really designed to do is to allow people to rapidly create their own detectors for things that haven't been in the detector already. So, for instance, if you're working on a particularly rare species, it won't be in one of these apps already. It's too rare. They haven't put it in there. But you might also be working on a more familiar species, but you'd like to divide the juveniles from the adults, or a local accent, for instance, of a bird song.
Birds do have accents, do they?
Oh, that's right. Well, yeah. I think that's right. They certainly have local variants on their songs, right? So you'd be able to track these sorts of things.
So how does bioacoustic modelling actually work then?
So the way Perch works is it brings in these audio data files, and they're huge. So lots and lots of data. And it crunches all that down into a much smaller amount of data, which is this so-called embedding. And then that embedding then can have all these downstream uses, the most obvious of which is developing new detectors. So you can think of it as a big kind of process that takes huge amounts of data in and crunches it down to a small amount of data that retains all of the salient signal that you'd want for understanding ecology and identifying species, and has thrown away as much of the noise as possible. However, there's also, for example, at least one other important use case, which is called search. So if you take different audio clips and crunch them down here, you can also then easily go and find similar audio clips. Because often one of the main barriers is, let's say you're looking to monitor some rare species and you put the microphone out for hours. Well, where's the chirp? You've got to listen to the thing for today. But if you can just find one or two here, then you can say, right, now I can find the similar ones because I'm looking for the ones that have got a similar perch embedding to these. And even a third one, which I don't mind speculating around, an idea I've been talking with a lot of colleagues about, is if you're looking to do something like verify ecological restoration in the field, you can imagine if I put microphones in a good place like a nature reserve and in some other place like my garden, I've been rewilding my garden, right? Then through time, you can see whether the perch embeddings, say in my garden, become more similar to the local nature reserve.
Okay, so wait, let me understand that then. So let's say you're doing a project where you want to increase the occupancy of a particular type of species. You can put a microphone in there and work out whether your intervention is increasing the population of the whatever it might be.
It's absolutely right. So there's sort of at least two scenarios to think about. One is, yes, if you're focused on one or more particular species, then perch can be massively helpful because you could develop detectors for those species. And we also know it's not just the species yes, no, but the frequency of the calls and even some of the variation in the calls. So in some cases, you can tell individuals apart, by the way, here. So we can say, is it one bird singing all day long, or do we have 4 or 5 birds singing? And perch can even help with that.
What that specific bird?
Specific bird.
Wow. Okay.
Exactly. Yeah, it's really important, right? To know. I've got lots of blackbird song, but is it one blackbird or is it 10 blackbirds? So in this way, you can use bioacoustics in combination with perch to increase your ability to measure not just the presence or absence of species, but the abundance and then the change in that through time, like it's getting more abundant. So that's one scenario, very species-focused view, and this is how most people currently approach biodiversity and ecosystems, is through this species lens, which is very important. But it's also interesting to me, and I'm sharing an idea here, right? I've shared with lots of colleagues, which is in some areas of the world where you've got a really high biodiversity and much less data, much less understanding, what you could do instead is almost view the perch distillation as a distillation of the audio ecology of a place, even if you can't identify all the species. And then if I pick a good place, like a local nature reserve, and I pick a place that I'm looking to restore, then I could just say, on aggregate, are the perch embeddings becoming more similar? And I may not know which species are involved. I've got all these things going, pops and clicks and whistles and et cetera. But in a sense, because what perch is, in a sense, is a kind of deep learning numerical answer to the question, what does the nature sound like in this place? And so if through time I could say my place is becoming, in terms of that sound, more similar to some reference place.
Well, let me ask though, because, okay, so perch, I mean, given the name, sounds quite a lot like it's mainly focused on birds. But can you put this into other environments? Like what about underwater? Does it work there?
So you're right, perch started by just classifying very large numbers of bird species. But amazingly, it turned out that then when they tried it underwater on these hydrophones, it seemed to work really well.
What, the same
Exactly
model?
The same model. Worked really well. And I think what this teaches us is that there's something around natural sound, the way that that's evolved, that actually has, now of course it won't be perfect, but has a surprisingly high degree of transfer into underwater. There's this whole area, right, of acoustic ecology. And we know that, we think there's evidence for the fact that species have evolved away from each other in terms of their use of the audio spectrum. Because easy to forget that most of the sound you're picking up in bioacoustics is deliberately produced by organisms, right? It's communication. That's what's amazing. They're communicating with each other. And just like us, they need to think about the spectral bands.
Well, they want to be heard.
Audio spectral bands. So, of course, they're differentiated. So it looks like...
So some use low sounds, some use high sounds,
right,
because you want to make sure that your communication is successful.
Yes, exactly right. So, overall high and low. And then you think about the temporal thing, is it like da-da-da-da-da-da, or is it ooh, ooh, ooh thing? So... you can imagine this has somehow evolved as an interaction, not just within species, right, communication, but between all the species. They've all responded to each other somehow and settled down on these different patterns.
And what do you find when you put microphones underwater? What do you get from these hydrophones?
So we've queued up actually a couple of sound recordings from coral reefs that I'd like to listen to.
Okay, go for it. I mean, some grumbles going on, some squeaks. Quite crackly as well.
Yeah. And then here's another one.
Much quieter. No grumbles. I mean, what does that say about this coral reef, though?
So maybe now it won't surprise you to hear that the first one of those was a much healthier coral reef than the second.
Oh, really?
So that diversity and richness of ecological sound, animal communication, is a strong indication of a healthy ecosystem, you see. And so even as humans, we can hear that difference.
Wow. So you really have like that richness of understanding the environment itself just from the audio signal.
That's right. So, and that's an illustration of how even just that overall, we can embed that overall signal in a way. That can just give us a general indication of the health of ecosystems. Of course, with more specific species data, we can actually start to tease out individual species. So if we're particularly concerned with endangered species, maybe even invasive species, right? We can pull out seasonal and daily temporal patterns in animal behavior. We can start to understand geographic differences in where species live, all just by dropping these microphones, in this case, into the ocean.
But this is an explosion in possibilities. I mean, because if previously you stuck a microphone underwater, you have to listen through hours and hours and hours of tapes and have no real way of it's basically the human brain trying to pick up on patterns.
Yeah.
But I mean, now if you can single out not just individual species, but individual voices, as it were, from particular individuals, I mean, that's gigantic, right? Gigantic potential.
Yeah, it's absolutely huge. That's why so many of us are so excited by the power of sort of bioacoustics combined with deep learning in this way, and especially with this foundational approach to bioacoustics that Perch is bringing. And it has at least two advantages that you've hinted at there. One is that it can just massively accelerate what humans could do. So you could take a problem that humans could do. It's just that you'd have to have hundreds of people listening to thousands of hours of audio. So, it's very, very inefficient. But you're right, there are also areas where you go beyond human capabilities. Humans are not necessarily all that good at passing out natural sounds or identifying species from sound. It's quite a hard skill to learn. And there may be cases like pulling out different individuals might eventually be even too subtle for humans to do.
Staying underwater for a moment, I mean, there are some species, I'm thinking about whales and dolphins here, where there is some evidence that their communication is sophisticated, right? Can you use these ideas for that? Can you sort of, I don't know, learn to speak dolphin?
I like to think that we will be able to talk to animals using AI at some point, and that these embedding foundational modelling approaches like Perch will be really important in that. But you'd need some other elements there. Interestingly, some colleagues of mine have been involved in producing this thing called Dolphin Gemma, which is a large language model that's been adapted to be suitable for beginning to decode dolphin communication. It takes the sounds, separates them out, tokenizes them, and basically brings it into the world of large language modeling. So that's an example of, it's early days, but that's an example of AI actively being used to study animal communication at a level that we really couldn't do before.
Thing is, I can see the potential for this in terms of scientific interest, but I do wonder whether, let's say we get to a point where you can understand what dolphins are saying, communicate with the higher animals on the planet. Does it change how we view ourselves and our place in the world?
I think it absolutely has that potential. I mean, most of the work we're doing at the moment, as I mentioned, sort of filling known information gaps in known processes, etc. But sometimes you think that the real change can come in the long run from these moments of awakening where people almost overnight can change their relationship with nature. And I think we've seen at least two examples in the past anyway. One was the first picture of the Earth on the moon. People often, and I guess historians can debate this, but they often trace some of the more recent increases in the modern conservation movement to that picture. When people looked at the Earth for the first time and realized there was just one in this dark universe and that all of us shared it together, etc. Another one is actually whale song. And this is just listening to whales. Even if we can't tell what they're saying, that really changed the way people thought about whales. And so the idea of being able to do that for more species with things like Perch, but then being able to decode that to say what they're actually saying and maybe one day even have some kind of conversation, and if AI can help to empower that, that might in the long run be the most powerful role of AI.
Well, okay, we've covered a lot of ground in this episode. So maybe I'll finish by asking about the future. How will AI change the kinds of questions that ecologists can ask?
So I think up to now, as we've discussed, amazing progress in our ability to monitor and extract data from the field and from the literature. Amazing progress, I think, in mapping and geo, which is only going to get better. I think the couple of the future directions to explore. One is, what if we really could confidently predict the future of ecosystems. All the plants, all the insects, everything, the soil organisms, the fungi, under a range of different scenarios. If I do this, this is what the ecosystem will look like in 10 years. If I do this, this will happen. And also in a way that took into account future climate change, etc. So these sort of future-proof, robust, conditional predictions of the future of ecosystems down at the fine grain. If we could do that, of course, that could unlock an entirely different sort of relationship between us and nature. We could use that simulation ability to then be able to find all the optimal ways that we should behave, identify the key trade-offs, which species to plant, build new kinds of regenerative agriculture systems, agroforestry with mixed species, where we've also got rewilding and we're also bringing the soil carbon back, and it's all robust to climate change. So if we could do that, then every person that's affecting nature or taking a decision that they think affects nature would be fully informed as to the future consequences of those actions. And that feels to me like an amazing potential. Of course, it would depend on values as well, but I would hope that on average, most people would use that ability to do good for nature.
Amazing. Drew, thank you so much for joining me.
Oh, thanks for the invite. It's been great, really.
I think it can be tempting to imagine that ecology is a bit of a niche application for AI, a nice worthy project that sits behind all of the big flashy advances like video generation and drug discovery. But in reality, this is just a few steps behind the others. They're still at the data gathering and data assimilation phase of the process. But the roadmap here is just as ambitious. And in the long run, I think there is real potential here, not to just use AI to conserve what we have already, but to completely change our relationship with the natural world itself. You have been listening to Google DeepMind, the podcast, with me, Professor Hannah Fry. If you enjoyed this episode, then do subscribe to our YouTube channel or leave a review on your favourite podcast platform. And of course, we have plenty more episodes on a whole range of topics to come, so do check those out. See you next time.